Welcome to another Samso Insights. Today I've got a special series on from the Geological Survey of South Australia. I've got Dr. Diana Zivak here, who is currently working on very interesting projects. Her topic is rare earths, but we'll be fairly wide-ranging in our conversation. I'm here at the core library here in South Australia. We've been here before. I had the conversation and a pets here in my previous conversation. So welcome, Dr. Diana Zivak. Look, we connected through the survey, and I think you guys got a lot of information that's coming out. And I think, obviously I've got declare my interest. I'm Director of Title and Resources, where we have tenements here in South Australia. And obviously my interest is trying to learn as much as possible. And I do find that the Gawler is actually really unrealised, and there's a lot of potential here, which is very obvious the more I sort of learn about the region. So you're a graduate from University of Adelaide, did your PhD here, now working for the Survey of South Australia. You've been around the traps a bit, but I'll let you explain.
Yep, sure thing. So like you said, I'm a senior geologist at the Geological Survey of South Australia at the moment. I've only been here 2 months. Prior to that, I've actually worked in mining industry, in coal mining, for about 3 years after my undergraduate, and then came back and did a PhD at the University of Adelaide, where I worked on sort of large-scale tectonics and amalgamation of southern part of South India, which was really good. After that, I've moved to Perth and did a postdoc there at Curtin University, and then I've come back to Adelaide and did a postdoc with the University of South Australia, and then another postdoc at the University of Adelaide prior to coming here at the survey. So my interests are quite broad. I always say to people, I'm a bit of a jack of all trades, master of none. I've dabbled in everything, from geochronology to geochemistry, structural geology, large, scale tectonic reconstructions to phosphorites, which I had to Google when I first when I first got the project. I was like, oh, what is a phosphorite? Google. I've dabbled in everything, but my interest really lies in looking at ways to vector into mineralisation. So during my postdoc, I used mineral chemistry and to try and find what elements substitute in different minerals when they're close to any deposits. I focused on gold with, for example, I looked at rutile geochemistry to try and vector into orogenic gold deposits, and we've discovered some really interesting results from that. And then I used monazite, particularly in, say, at Karapatina, to try and see whether we can find some sort of vectors towards the mineralisation, and whether we can find those signatures in the overlying cover. As you know, Gawler Craton is, 75% of it's covered. So finding ways to try and find whether we get these orogenic systems dispersed in the cover and how we can detect it was one of the objectives of my previous postdoc at UniSA. And we used monazite for that and Karapatina as a test site, and we could see that the signatures were actually, you can detect them 2 kilometres away from where the actual deposit was, which was really exciting. And then in my postdoc, just before I started the working at the survey, I looked at the rare earth mineralisation and potential of phosphorites in the Georgina Basin in northwest Queensland. And that was really what really got me started on this rare earth story. And, with critical minerals now being a hot topic, there's rare earths everywhere. There's so many companies popping up with, different types of rare earth deposits and clay hosted. That's a big thing, particularly in South Australia anymore at the moment. There's a lot of companies reporting clay hosted rare earth deposits in Western Australia as well, particularly around the Esperance area. So these are, the kind of hot topics at the moment. So I thought, I'll go in a bit more detail. And, with the survey, I'm basically my whole project is to map the prospectivity of South Australia for rare earth elements. So it was a great opportunity for me to do that, to satisfy my own curiosity about the rare earths, as well as help out and, give something back to the community, the investors and the companies to try and maybe find some new targets.
It's because looking at your experience, I mean, obviously you've been around, and I'm a proponent of jack of all trades, master of none, because that's where you gain your experience and then you hone in on certain things. But noticeably, you had a lot of work in the analytical part of stuff, which is really important because as geochemistry, as you pointed out to me, I'm on board with that. Geochemistry is the lifeblood of discoveries. Geophysics and everything is fantastic for targeting, but it's always the truth machine. The drill comes and we look at the chemistry after that.
Yeah.
So it's they all go hand in hand. Can you share us that journey, your experience, your thoughts on how where technology is today in terms of the analytical part of it, the understanding of the geochemistry in terms of, let's use obviously rare earths, and what do you think is going to help us going forward, or may help us?
Yeah, I think it's come along a long, long way, even since I started my studies about 10 to 15 years ago. Primarily, I think at the moment, data science is the biggest thing, right? So the biggest technological advancement at the moment is AI. So machine learning for geochemistry is going to be a big thing coming up. I think that's probably something that we really have to get our skills developed in. But again, machine learning is always a bit tricky. It's what you get out is always as good as what you put in. So we still have to have those basic analytical things really worked out really well. And with analysis, for example, people look at what we've developed in terms of getting geochemistry done in situ, for example. The speed of when I did my undergrad, I remember sitting in a basement on the laser, purging it between, each spot on the analysis. If I do geochronology in one spot, I'd have to purge it, then I have to do it again. Now you automate everything and you can get thousands of analyses in a day. I think Curtin University has just developed a method where they can analyze up to 4,000 analyses a day. So it's just the speed at which we can get things done and accurately, I think, has improved massively. The new type of technologies are coming out every day. I think, PXRF wasn't a big thing really when I was going out. That's, now you can go out in the field and just measure geochemistry there in situ. LIBS, again, is another thing where you can so laser-induced breakdown something or other. I'm terrible with the acronyms. But, you can go in and measure the chemistry, and particularly lithium. So LIBS is really good for lithium being a critical mineral that we all need. So you can do that stuff in the field a lot more readily now. And here in South Australia, I don't know if you're familiar with DAT CRC prior, and now it's Minex CRC, the big cooperative centres that have worked on coal tubing rigs, where you can have, basically you analyse geochemistry, time in flight geochemistry. So as you're drilling, you're getting geochemical data back. So that, I think, is also quite an interesting and really good advance for explorers going in and drilling now. You don't have to wait for the chemistry to inform where you're going to drill next or what you're going to do next as well. So there's a lot happening, but I think we're getting so much data back at the moment. We almost have too much. We have to figure out how to process all that information. I think that's where data science and machine learning is going to be quite big.
Let's get into the rare earth side, the clear rare earths, because obviously that's the talk of the town. Even on the Samso platform, I've had, over the last month about several videos just on the topic, and I remember my very first time I had a OD6 metals. Brett Hazelden. I said, Brett, you got to explain to us what all this means. What is a good intercept? Is 10 meters good? Is 20?
Yep.
Do we need 50? Do we need 100? And your parts per million, is
Yeah.
300 good?
Yes.
500? 1,000? 2,000? No idea,
Yep.
and I had to go and learn what TREO was and
Yep.
and all this kind of stuff. Now today, we're kind of matured to a point where we go, okay, we get all that now.
Yeah.
And now it's all about metallurgical issues.
Yes.
Then it went from easily leachable, ionic, non-ionic, and then now it's like, okay, it's really the economics that really plays, because if you got a big resource, you can beneficiating, they're all doing all that kind of stuff. So the process is matured, is what I'm trying to say. So in your, like you mentioned, the Esperance region, because I'll just give you my view. The Esperance region to me is like the bulk center. So you get a lot, and if everyone played together, then you could be the place where, if Australia wanted to value add in this sector, this is the best place to be. So what's your opinion on all those comments?
Yeah, so you're right on everything you said. When I started looking into clay-hosted rare earths, one of the things that I think a lot of companies and, going into, we didn't really know much about clay-hosted rare earths here in Australia. We never really explored for them. And it's only in the last 3 years, I think, where this explosion of clay-hosted rare earths coming out everywhere. And what we're finding out is that the story isn't as simple as what we've been taught. In China, you have the typical your ion absorption clays that are rich in the heavy rare earths, which is what a lot of the companies are interested in. They're probably more higher value. Their clays are obviously ion absorption, where your rare earths are absorbed onto the surface of the clay. And when we started doing that here, we found that that is not the case. The rare earths are hosted in secondary minerals within the clays. So they're not your sensu stricto ionic absorption clays. So I always, like you said, use the term clay-hosted rare earths. And when we look at, I guess, from the geological side of things, I think we know there's a lot of metallurgy that's been done. So a lot of ASX releases that you read from companies will have what the percentage of rare earths were leached using what acids and everything else. And I'm no metallurgist, but I know one thing, that you are not going to get maximum unless you do the mineralogy. And that's one thing that's lacking in most people I spoke to, most companies that I spoke to. They do not understand what minerals are there within the clays. Part of that is because trying to have look at the mineralogy of clays is very hard. If you want to put a clay in a puck and polish it nicely, as you know, clays, they swell, you can't use water, you have to use something else. So there's a difficulty in analysing where the rare earths are sitting within the clays to inform the metallurgy. So metallurgical, they're quite expensive. You send off a sample to ANSTO, it costs a lot of money. So, companies are selecting a few of the samples to do it. And then, of course, the parameters that change are always the acid, the temperature, whether it needs to be, mixed while it's happening. So, but nobody's doing mineralogy. So we have, at the moment, very poor understanding of how these clay-hosted rare earths form. And one of the things that, particularly at Esperance, for example, I think Mount Ridley Mines, they have, a massive area where they have clay-hosted rare earths, but it's not all over the same basement rocks. Copper mine is on top of a limestone, right? So you have the petrotherm, they have, so for example, meteor and comet prospects that are on top of, intermediate to mafic rocks. You go to, say, Apollo with investigated resources, their clay-hosted rare earths are sitting on top of felsic volcanics. So we do not have at present any understanding of what exactly controls are good grades. And like you said, what are good grades? In an ion absorption clay in China, 500 to 1,000 ppm is a great grade because you can easily get most of it out. I think in somewhere in Brazil, I can't remember exactly, it's top of my head what the name of the mine is. They've got 3,000 ppm rare earths, but they only extract 30%, and that's enough for them to be economic. Depending on the price of the element you're extracting. If you have heavies and you have 3,000 ppm, you only need to extract 30% for it to be economic. So it's a bit of an exercise to work out exactly, how much it's going to cost to mine, how much it's going to cost to extract, and how much you need to extract. So when you talk about grades, the grades can vary a lot. And I think that's part of the reason why we don't have like a cutoff, or this is a good grade, is because we don't understand exactly how cheap it is to extract. You have to do a whole process to calculate, okay, if I extract 40% of my rare earths from 1,000 ppm, it might be economic depending on what acid you use, how easy it is to just, whether you heap leach it, whether you just get an excavator and just heap leach it, and all those questions. So I think company will need to, if they're going to explore for clay hosted rare earths, they're going to have to go in and just do their own thing in a way. And I'm not saying ignore other models, but do their own investigations on their own projects, because one of the things that we need to start doing a bit more, and I know that this is happening, there's a whole bunch of projects that have been also funded with on the academic and industry side. There's a collaborative projects that are going to investigate these questions. They're going to look at mineralogy. I know we have a very, very good researcher here, Dr. Laura Morrissey, who's been looking at, in South Australia in particular, on the peninsula, she's been investigating, these clay-hosted rare earths that form on top of these granites and where the rare earths come from. So, you have, say, minerals that are within the granite that have the rare earths like apatite and titanite, and what she finds is that these minerals disappear entirely when weathered, meaning that they were dissolved and the rare earths are now sitting in the clays that are developed on top of them. At Coppermurra, the clays are sitting on a limestone. So these clays...
This is AR3, yeah?
AR3, yes, sorry. So that's an entirely different deposit to your typical clay-hosted that form in situ or weathering or whatever the basement rocks are. Could be even mafic rocks, right? So they're sitting on the top of a limestone, and these clays obviously were transported. They didn't form in situ. They form near the base where the clays basically hit the limestone, and it's that interaction that basically causes precipitation of these secondary minerals. So they're not ion adsorption clays. There might be a small portion that's adsorbed, but not very much. These rare earths, again, are hosted in secondary minerals as well.
But the enrichment is after they got there, or the enrichment is before they got there?
Enrichment was before they got there.
Rare earths.
Yeah, so the rare earths, there was a really good researcher at the University of Adelaide who's worked on it. And what he found and how he found that these are being transported is he's done a neodymium isotope study, and he found that the neodymium isotopes reflect the surrounding terrains. So the rare earths were there in the beginning, but they weren't distributed near the base. So it was, from my very poor understanding, and Stefan will kill me when I butcher his research.
Butcher it.
Butcher it. Is during deposition and formation, where it formed these sort of kind of little estuarine environments in the coastal settings. Yeah. The rise in level and the pH of the water basically controlled what clays developed and where rare earths were concentrated. That is much as I know. If we're going to go into detail, I don't know.
Yeah, I was at the talk.
Yeah. But certainly it was the processes that happened during the deposition that controlled where the rare earths were sitting in that kind of environment. And hopefully that will be published very soon, and then whoever was interested can read that. But again, I'm just saying, with clay-hosted rare earths, it's going to be very hard to narrow down, do I need to look for a felsic rock and clays developed on top of a felsic rock, or do I need to look at a mafic rock?
Yeah, I'll stop you there because I've got a question. And the question is, obviously, I think I've seen, obviously, through my conversation, felsic rock, mafic rock, granitic rocks, limestone in this case. And I spoke to someone who said they were in sediments.
Yep.
And everyone's slightly different in terms of grade or composition and things. So my simplistic thinking is that surely the geological control must have some sort of effect on what you get. But on top of that, I think the geomorphological thing, part of it, whether it acts as a trap or a host, or it acts as a conduit for enrichment to happen. So that combination must be in play, because otherwise everything will be homogeneous.
Yes, yep.
Like alluvial gold, for example, but it's not. It's not because you're getting different grades, you're getting different. Well, like OD6 and those guys, they've said there's what you could term refractory and non-refractory parts of their project, and I think that's again, and then you're getting recently Venture Minerals announced they got like 40-50 meters at close to 2000 ppm, and certain parts of it's about 2500 ppm, and it's in the sort of like non-weak belt area, not where the Esperance is. So the geology is slightly different again.
Yeah.
Where that means in extraction, whether it's easily, that's their next step, obviously.
Yeah.
As you say rightly, is everyone's unique in that deposit, right?
Yes.
So do you agree that all those combinations has to be a control there somewhere, right? It can't be just magical that you have this randomness.
Yeah, I think so too. I think firstly we have to have a source of the rare earths. So you have to have minerals or something that breaks down to release those rare earths in the first place. I think geomorphology plays a big part. So I think you look at I think Cobra Resources, their new model is to look at paleo channels and the mobility of rare earths in groundwater through paleo channels. So this is a big question that I had, is how do you mobilize and where do you mobilize and concentrate the rare earths in the in the clay hosted? So first, obviously, we need the source. Yep, that makes sense. So could be rare earth rich granites, or it could be anything. And then if they're going to move in groundwater, we need to start thinking about, are they moving in paleo channels, where they're going, what kind of groundwater mobilizes them. So I know, for example, that in rare earths in groundwater, they're mobilized by two things. One of those things is carbonate complexes. So they've like formed carbonate complexes in water, and also humic substances. So, to mobilize them and what the concentrations of these rare earths are in the groundwater, we don't really know. They're not going to be very large. So I think we have to think about the source first. They're not going to move very far from the source. That's what I think. My opinion is that I don't know. That's just what I think in terms of there's too many traps around. So, and the traps can be a different type of groundwater fluid. They can be reduced by the rocks. There's too many interactions, but they won't move very far from the source. So even if you are looking at, say, granites and you have a paleo channel next to it, that's a potential where you might find, say, rare earths. Obviously, for in situ weathering, you want to look for any minerals in that basement rock that have rare earths that can easily be broken down during weathering. That will release the rare earths. So the other, you mentioned sedimentary rocks, and that's another interesting topic, is that I think Taruga minerals in Flinders Ranges here, they found clay-hosted rare earths in a quartzite. So these clays develop on these quartzites. But what's really interesting is they're proximal to this diapiric intrusion, so these massive salt diapirs that have risen through these sediments and now occur basically throughout the Flinders Ranges. And this is sort of, I think, almost the first type of the clay-hosted deposit that we know, because these sort of clay-hosted rare earths occur along the margins of these diapirs, and we have no idea why. And there's so many of them in the Flinders Ranges. So one of the things that I'm interested in and I'll be looking into is that I'm going to be going to target these sedimentary rock packages next to these salt diapirs, which nobody's looked at before. It was only an accident, well, not really an accident. I guess the Taruga minerals, they can tell you how they managed to zone in and find these rare earths, but certainly they're there. And we don't know whether they occur everywhere, but I think the main thing is the source, whether it's the fluid or, I think you have to have the rocks that are or maybe even, I guess you can look at faults and fluid movement along faults as well, associated with intrusions as well. And that's another topic. But for the clay host, the rare earths, you have to have that proximal source somewhere, I would say.
Obviously, the value in the clay rare earths is the heavies. Is there a way, or is there a theory that this is what you should focus, or this is where you should go if you want more heavies in your clays than not? Because the value proposition is significant by having a little bit more heavies over the lights.
Yeah. Yeah, so there is. The lights and heavies fractionate out by the processes in the groundwater. So heavy rare earths, they like to stay in solution in groundwater. So they typically form closer to the base of your sap rock. Your light rare earth elements like to absorb onto colloidal particles much more readily than the heavies. So there's this almost, in a weathered profile, you have your lights maybe in secondary minerals or absorbed onto the colloids, and your heavies are sort of more enriched just below it.
So the lights are the promiscuous ones.
Yes, yeah.
And the heavies are
they like to stay in water.
They're the ones that wife material.
Yes. Exactly. So yeah, and I think that's just a even in seawater, that's what we see is for example, I'll give you an example of phosphorites. Phosphorites are enriched in heavy rare earths as opposed to light rare earths. And the reason for that is that when they enter the marine realm in your seawater column, you have the lights, again, they absorbed onto little colloidal particles that are floating around in the water, whereas the heavies stay dissolved by forming carbonate complexes with water. And when you precipitate the carbonate fluoraptor, which hosts the rare earths in the sediments, in the bottom sediments, they will have that signature of the seawater, which is enriched in the heavy rare earths. So if you wanted to go for heavy rare earths, I would say go and look for phosphorites.
Okay.
Yeah. So that was part of my research at other universities, looking at the phosphorite deposits in the Georgina Basin. And this isn't as simple as it looks as well. It's not all phosphorites are rich in rare earths, and that was one of the questions I had. What controls the enrichment of rare earths in phosphorites? At first, we thought it was the basement. So if the phosphorites are sitting on, say, sedimentary, carbonaceous sedimentary rocks that don't have many rare earths, as opposed to if the phosphorites would deposit on top of, granites that are rich in rare earths, which in the Georgina Basin has this sort of, you have the Lawn Hill platform, which is carbonaceous sediments, and the other part of it is sitting on top of these sabella granites that are really rich in rare earths. And I thought, well, maybe it's the basement control where you get the groundwater interacting with the basement that's rich in rare earths. And then you have the coastal areas where those groundwater seeps out into the marine realm and enriches the water in rare earths, and you form phosphorites and they absorb the rare earths from the seawater. Turns out that's not true. So that was our hypothesis going into it. But what we discovered using isotopes to trace the origin of rare earths in these rocks was that it was the seawater signature, completely Cambrian seawater that basically came in and transgressed onto the continent. So it was an epicontinental sea during the Cambrian. And we know this because the actual signature of the phosphorites on endymium is much more radiogenic than the basement. So it had to have come from somewhere else. And that was really good. But then we had the issues, if it's the same seawater, why are some phosphorites rich in rare earths and others are not? If it's, presumably the same seawater. Well, what we found is we looked at sequence stratigraphy, and we found that some of the deposits formed earlier and they weren't as rich in rare earths, and they formed these sort of what we call it's called a microspherite. So it's basically
rich in rare earths or lights and heavies, just
all of them.
rare.
So all phosphorites are enriched in heavies. So they typically, unless you go through diagenesis, then they're rich in mid rare earths. But neodymium, again, is a highly desirable element anyway. So even if they're rich in mids, they're still pretty good. But heavies usually is where they're really rich. And what we found was that they formed earlier, and then during the main transgression is where all the high rare earth phosphorites were deposited. But that wasn't the only control. So if you form a phosphorite in situ, it kind of forms this sort of, you can't even see the pellets. There's just like a homogeneous phosphate mud, if you think about it. And then these prospects, or these deposits further south, they were grainstones. So what happens is you form these phosphate muds in situ, and then you move them around with currents, and you form these grainstones. And it's the time that these pellets spent in the seawater that was another main control on why you had so many heavy rare earths, because you have a high mass to surface ratio, and the rare earths keep absorbing, and they get enriched in the rare earths. So you have to look for grainstone phosphates. They're always richer in rare earths. And also you have to look at the sequence stratigraphy and do this. But that's more detailed work. For now, if I was to say to explorers, look at, phosphates and phosphorites, I would go for grainstone type. So where you have little pellets. They kind of look like sandstones, really, when you look at them. But yeah, they're really quite enriched in rare earths. So
Kind of just looks like a rock.
it does. It looks like, you look at it, you would think it's a sandstone. Every now and then you'll see a little fossil, like, oh, okay, that's not a sandstone.
Yeah.
But you look at it and it's like, just little pellets everywhere. So, yeah, very hard to mistake, especially if they're quite grey. You think they're sandstone, but they're just carbonate fluorapatite. That's it. So more than 18 to 20% weight percent phosphate means it's a phosphorite. Yeah.
So let's go up a step in mineral exploration. I guess I have always said you need to look for a mineral system. Everyone in generality talks that look for the mineral system, and therefore you have the potentials. Comparatively, the Gawler is not creating a lot of mines. And why do you think the Gawler is not giving up its secrets so easily, or it's not giving up its secrets, or what's the reason?
Oh, that's an interesting question. Quite a hard one. I think we get focused on certain commodities. I mean, Gawler is known for its copper, right? So, ISCG province. So I think there's a lot that we've seen that we don't realize we've seen in a way. We miss things because we hyper focus on a certain commodity. The other issue with Gawler, as you know, and I think probably WA would be the same in some parts, is that it's so remote. So infrastructure is not there. And to make a deposit economic, you really have to have that infrastructure in place in order to be able to extract that. So it's a high risk project for an exploration company to go into the areas that have been underexplored and to go and try and find something without having the infrastructure in place in the first place. So I think partly that, but also partly because we overlook things because we hyper focus on certain things, like with ISCGs. Everyone's copper, gold sort of province. That's what we're targeting when most companies go in and target. But I think that's changing now. I think the other thing that we also do at the survey quite well now is that we are now in the process of digitizing everything and creating these seamless digital geology maps that explorers will, have access to, and then, go in and I guess create better targets in a sense, and maybe de-risk some of the issues that they might have. So I think in that sense, we've improved a lot, and we're improving every day in offering that. And hopefully now with the critical minerals, I think a lot of companies are now realize that they've missed things in the past. Say you're looking for uranium, but then there's a chock-a-block full of rare earths, but you didn't care about that at the time. I think that's changing now. I think we're going to see Gawler becoming a bit more open in the sense that there are a lot of mineral systems. It's hard to know why we haven't found the big one, like, the Olympic, the massive world-class deposit yet. It's there, but, cover, infrastructure, everything plays a part in why we haven't done so well. So, we have a couple also protection areas, like Women Protection Area and the APY lands that haven't really opened up, but, in the future, who knows how that's going to go. So, Yeah, Gawler in itself, I think, is only now sort of starting to light up, particularly for clay-hosted rare earths. I think there's a lot of potential there. There's a whole bunch of companies now that have found quite significant intercepts of rare earths. One tricky part with rare earths in IRCG systems, so South Australia, I guess at Olympic Dam, they have one of the largest resources of rare earths in Australia. They've got, I think, it was some ridiculous 1.3 billion tons at 0.3% total rare earths. So that's about 35 million tons of rare earths sitting there. The trouble is that processing is very, very tricky and quite uneconomic for BHP at the moment, partly because the mineralogy is so complicated. You know, and this is, I think, something we really overlook with rare earths, is that mineralogy is key. You really want a sort of monomineralic deposit. You know, one mineral, ideal, and that's it. You know, whatever it is, I'm sure we can find a way to get rare earths, but as long as it's one and it's easily beneficiated and you can do that. Unfortunately, with IOCG deposits, it's going to be very hard to do that. You've got different types of minerals that can be quite fine. I think that's one of the issues that the BHP would be having, is that they're really, really fine fractions. So they come out in slimes and different parts of the metallurgical process and copper extraction. So you really, to open up Gawler, you really need to be economic in terms of rare earths. I'm talking like there's potential for other critical minerals that we haven't really discussed, base metals and things like that for sure. But in terms of rare earths, I think we still have a long way to go in understanding, the mineralogy and the mineral systems of the Gawler. IRCG we know quite well. We know what minerals are there, but the metallurgical side is going to be a problem. And so I guess that's one of the things that's going to be one of the key questions going forward.
I mean, Olympic Dam is a mega deposit, and in some ways, a lot of the conversation I've had people is that there's so many piles of, and you yourself mentioned that 1590 is the starting date, but there's so many other fluid actions which are much recent and things like that.
Yep.
And once you've cooked things so hard, it can complicate things.
Yep.
So I guess it's the monster that everyone compares to, but then you got the Carapatinas and Prominent Hills and the I think Oak Dam West or something like that.
Yep.
They're much smaller. I don't know the complexity or simplicity, whatever. But I guess there are still anyone who find one of those should be more than happy.
Yeah. I agree.
And Havila's got 200,000 tons of tin sitting there, and there's gold. But no one seems to talk about all that. Everyone's things like, the three big ones, right? Olympic Dam, Carapatina, Prominent Hill, things like that. But no one talks about, even Challenger's kind of like lost, but that's a high grade metamorphic gold mine, which is unique, produce a lot of gold at its time.
Yeah.
But it's sitting there by itself, and the nearest neighbour is probably Tankilia, but not quite there yet. Then you draw another 100 odd kilometres, then you hit the IOCG belt, but anywhere in there, it's kind of like anything can happen, right?
Yep. I think if you want to open up Gawler in South Australia, build a refinery for rare earths in SA and see what happens. I think we lack the downstream processing. So for any company to start up, processing rare earths in South Australia, they're going to need to be the first, and it's going to cost a lot of money. So you would have to have quite a significant deposit that is really quite good grades and quite continuous, quite big, a lot of tons to be able to justify doing that. But if you had that in place, then you can open up for a lot of the smaller deposits to start coming in as well and coming on board. So it's just hitting that first one. So that's why Olympic Dam, Carapatina, Prominent Hill are so successful, is because Olympic Dam have the refinery, they refine everything. Now BHP and Oz have merged, or they've taken over. So that's essentially one company now, and they've got all the facilities there for processing it. But we don't have anything like that for rare earths. at the moment. Coppermara, the AR3, I think they're doing small pilot testing to see, they produced, I think, one of the releases they released a couple of months ago was said that, they produced a concentrate of rare earths, so that's a good sign. But really what's holding it back is having that capacity here to process to create the rare earth concentrate. In Western Australia, you've got the Iniaba stockpile and the plant there, refinery. That's going to be, getting stuff from the Browns Range, which is another really unique type of deposit. It's quite, localized in Australia. I haven't really read many worldwide deposits that match that one. But it's, again, monomineralic with xenotime being the main mineral. So I think that's kind of the hold up a bit here in South Australia and kind of the eastern states, really. We, everything's... you guys have everything in WA. Yeah. But I think, we really need to hit that big one, good one, to be able to justify having, processing that here in South Australia. So...
Yeah, I think my biased thoughts is that probably the next, if there was going to be a rare earth hub, you'll have to be what makes sense would be in Esperance, because everything is there. And you got the size, the economic sales, but I think that, to me, South Australia is just opening up, because and I've benefited from the data coming out of the system, obviously for my own company and things like that. And suddenly you're saying, wow, the potential's there, potential for discovery. We went into this whole story with one theory, and then now we're thinking, hey, with all this other stuff that's coming up, we're talking Grisons, we're talking potential tin, and then if that's the same kind of system, then suddenly, hey, we could... other metals could pop out, other than the copper IOCG story.
Yeah. Oh, I agree 100%. And the other thing that I think we really need to start thinking about is that, multi-commodity processing. So, we have your main commodity and then your byproduct, which can really sort of value add to the whole project. I know, for example, at Port Pirie, the NISTA are now looking into basically processing things like zinc and more base metals as well. So we've got smelters here in South Australia as well that can probably treat some of the more base metal type projects. But, with these mineral systems, it's not always, you have main commodity, but you have so many byproducts. I think going forward, for me at least, I would think we need to start thinking about how we beneficiate and the metallurgical process aside to get most of what we have there already. Some of the critical metals that are on the list, like, for example, cobalt, nobody's really looked at before, but cobalt can be quite common in pyrite. So, if you're looking at copper and you've got a lot of pyrite, it might be quite cobalt rich. So can we produce cobalt as a byproduct? So for the project that you mentioned as well, if you've got tin or you've got tungsten or whatever you have there, on its own, it might not be sufficient. But if you've got something else to go with it, some other critical metal that can be extracted during the same process, then, that's something that you can take into account as well. Obviously, in your, feasibility studies or whatever you do. But I think, when exploring, you mentioned that I think we had a chat about it costs a lot of money to analyze a lot of elements. Sure it does. I agree with that. But I think that's another thing, that the cost of that has gone down as well, of analysis. So, for rare earths, you can just analyze lanthanum and cerium, and, go for your main things. Obviously, that, if you want to look at critical minerals across the board, there's a list of 21 elements. 61 cents per element per sample is really not that much, and you can target your main commodity, but then also have a couple of samples where you have the full suite just to get that representation of what still is there and keep your mind open. I think hyper focusing on a certain commodity is okay if that's what you want to do, but I think it's nowadays with so many technological advancements that we have, I think it's a good idea to open that scope to open our mining practices to not just extracting one thing, but looking at the holistically, what else can we get out, economically out of these deposits.
This might not be in your field of expertise, but is there any, because lithium's a big word now, right? Everyone wants to find lithium. Is there lithium in South Australia for all those guys out there that's watching and thinking, and where should
Yes.
they go?
I wish Jared was here. So he's my former colleague. He's a lithium pegmatite specialist.
Okay.
And I'll probably butcher his work as well. So certainly, yes, there are definitely potential, lithium pegmatites around South Australia. Looking from just going back to basics and mineral systems. There was a recent talk, by Catherine Goodenough. She's a director at the British Geological Survey, and she's works on lithium pegmatites all across the world. And one of the models she recently proposed, or sort of, we have the typical model where you have, granite is fractionating, you have magma fractionating, and it fractionates out to these pegmatites that are rich in lithium. So that was the typical model. But what she's done is proposed an alternative model, which is basically where you have melting of the crust. So during metamorphism, you melt the crust, the sediments, and that's what produces the lithium pegmatites. Now, looking at South Australia, we have a lot of granular facies metamorphic rocks where this can be the case. It's the question then becomes is where are these lithium pegmatites associated with these collisional settings, and where they've accumulated in high enough amounts that we can mine it. So the potential is there. If we were to go by that model of crustal melting, definitely, most definitely. I think there's a couple of pegmatites we are actually going to go out in the field and check out in October with the survey and in collaboration with the University of Adelaide. And that's going to be in the Curnamona province. So I think I'm not aware of any lithium pegmatites in South Australia at the moment, but if we're going off of the model and everything, I think we have a lot of potential to have these lithium pegmatites in South Australia. We just have to look.
One of the conversation about this is that you want a certain type of granites, and I noticed one thing I've noticed in South Australia, you have a lot of these Hilteba suites of granites.
Yeah.
How many of those could be that type of granite?
Well, if that's the model, if that is the correct model of formation for LCD pegmatites, it's hard to tell. I think the biggest control will be the mantle from which these magmas derive. So if you potentially have metasomatite mantle with lots of incompatible elements, so lots of volatiles, then when as you fractionate, you leave off all the volatile elements or like lithophile elements, then you can form these types of granites. It's the trouble is we really don't know which model to follow at the moment with this crustal melting model as well. You don't need a magma, you don't need a granite. So if that's the case, we have to be open to it. And certainly Catherine's presented very good evidence to suggest that it is mostly crustal melting. Again, if you have granites and those granites interact with the sediments around them as they crystallize, that might be the driving force for getting lithium out of the sediments and into the magma. And at this stage we don't know, but for Hilteba and that whole suite of 1590 granites is really quite prospective for lots of things. So I wouldn't be surprised if there's a lithium little offshoot every now and then. I don't know. It could well be. But I think it's very hard to find that control. We still haven't found the lithium pegmatite, but whether that's because we haven't looked previously or because it's not there associated with Hilteba, maybe it's something else that we need to revise, like melting of crust. Who knows? Yeah.
Interestingly, there's excuse me, I haven't come across a lot of literature that talks about other mineralization style that comes from the Hildebrand suites, but other than they're associated with the ICG guys and things like that. Is that something I've missed, or do you think that's just it's correct that there isn't a lot of other mineralization style associated with that kind of?
I think, well, there's uranium. So uranium is quite, I mean, even Olympic Dam is really quite rich in uranium. So uranium and rare earths are certainly there. As far as, if I was to go down the list of elements, obviously the base metals are not there. The base metals you want to look for volcano sedimentary kind of things. But, for IOCG, certainly uranium and rare earths are there. So at the moment, you look at the IOCG province in, along the eastern margin of the Gawler Craton. But if you reconstruct everything back to where these things formed, you have the Mount Isa and that whole IOCG province as well was all linked, as well as the Curnamona here in South Australia. So the Curnamona province was part of that Paleoproterozoic to Mesoproterozoic, and we have a whole bunch of Mesoproterozoic or early Mesoproterozoic granites intruding into the Curnamona as well, the sedimentary packages there. And we haven't found the big IOCG deposit in the Curnamona at the moment, but certainly we have some rare earth occurrences there that are all occurring with uranium. There's a couple copper gold. There's the Kalkaroo deposit there. But there's one deposit in Mount Victoria, or Prospect, I should say, that's got 2% rare earths at the moment. So, and, it was a uranium target initially because you have these kind of almost pegmatitic rocks with quite large uranium crystal or branorite or whatever they are. But the rare earths are there. We know from geochemistry we have 20,000 ppm, so 2% rare earths sitting there, but we have no idea whether they came in with the granite, whether there was some sort of fluid movement during metamorphism. There's the Curnamona has also been affected by the Alice Springs orogeny, so much later with this retrogressive shear zones that have monazite in them. So there's some mobility of rare earths even after that. So granites are important, I think, to introduce the rare earths and the uranium, the copper and gold. But then what happens after with, different orogenies post-dating that and mobilizing those elements is another question as well. So, yeah.
Closing comments. How do you, for those guys out there who, I'm unconverted, so I think, South Australia's, Adelaide's a great place. South Australia's, things seem to be working in place. The West Australian government's now revoking the new Heritage Act.
Yep.
And so that's put them back on better grounds
Yes.
to some degree.
Yep.
So for the explorers out there who would love to look at it, hearing the prospectivity, there's heaps of new data that's been put out by the survey, and I think that will create a lot of follow-on in terms of prospective areas and things like that. What's your closing comments to those topics?
So I think, the survey is going through a very good thing with digitizing everything. We'll be releasing a whole bunch of new data out there for explorers to use. There will be new little short series on critical minerals that will help explorers understand a little bit more about these systems and what to look for. I think keep an open mind. There's so many prospective areas, and just because we haven't hit the big ones doesn't mean they're not there. I think part of the reason that we haven't really looked for them in the past, we looked at certain things but ignored others or didn't really think about them, and so there's a lot of potential here. We have if you go back to basics and look at the geology, everything's there. The mineral systems potential, it is there. So don't shy away from asking lots of questions. Don't shy away from coming up to us and asking us questions, asking if we have any pre-competitive data that can help out. That's what we're here for. So I think there's a lot to be discovered. and hopefully we can help in some small way. And we will over the next couple of years. The big digitization project is going to be really, really good for explorers out here in South Australia looking for stuff. So if you want to know more about rare earths, please feel free to reach out. I can talk about rare earths all day long. I'm going to be doing a big report on rare earths potential in South Australia. So that's my job. It's going to be a big report that's going to go out there for the industry to have a look at, and hopefully that can help everyone out with targeting and finding some really good deposits. And
When's
then hopefully
that going to be released,
well,
potentially?
so it's a 1-year contract I'm on, so mid next year.
Okay.
Hopefully that's going to be out. So yeah, hopefully by then we'll.
And I'll edit first and get all the ideas first.
Absolutely, it's going to be all released in one. So we'll send you the copy as soon as it's out, so you can have the first look for sure.
Look, guys, I think South Australia has great potential. I think I'm our Titan is here, and I guess you're listening to the converted. It is a great area. It's a big area, and you know everyone talks of thousands of square kilometres in acreage when they're talking tenements. So again, as thanks to Diana, and I'll have all your details on our blogs and that goes out, and feel free to contact her. She's resident rare earth expert, and I'm pretty sure she has a lot more to share, but obviously we have to stop somewhere.
Yeah.
and obviously we can have part 2. So again, thank you, and till next time.
Yeah, absolutely. Thanks everyone.